Okay, so here we are, April 9th, 2021. Okay, so assignment 4 is due this evening at the end of the day. We will continue to work through lecture set 7 today until the conclusion of the class. And we have our final exam on April 16th at 9 a.m. So today, as I said, we'll continue to work through lecture set number 7. We'll just get as far as we get. If we finish it, great. If not, that's okay too. On Monday, we'll do review for the final. So we'll go over, effectively what I'll do is I'll go over what we covered in the class. I'll talk about what you can expect on the test. Time permitting, I'll go through some practice problems, and I'll take any questions that you guys might have about the final exam and about particular topics from the lecture. The only assessment that we have left is assignment number 4. And again, that's due this evening. So you guys have all of your quizzes back. You have the first three assignment marks back. So everyone should have a pretty good idea of where they're standing in the course in terms of what their grade is going into the final. It's particularly easy to compute your grade going into the final for this class because you only have the quiz assessments, which are 30% of your grade, and the assignments, which I think are 40% of the grade, based off of the course outline, right? So you can just take each of your marks from that, from basically each assignment and each quiz is worth 10%. So you can just take what you got on that assessment and work out how much of that 10% you've earned to date, and then just add those together. So it's a pretty straightforward calculation in this case. So again, everyone will have a pretty good idea of what they're going to have going into the final. I think the drop date is Monday. Usually it's the last day of class at McEwen. So hopefully the assignment 4 is turned around before Monday, but I'm not going to make any promises. I mean, hopefully the TA is able to turn it around quick. Yeah, sorry, that's right. So I'll choose the best 2 quizzes going in. So I guess 15% per quiz in that case. Okay. So I wanted to start off just by asking if anyone has any questions about the 4th assignment before we get into the lecture material. All right. I'm not seeing any questions. So, all right. So I'll just get started then. So last class, we finished lecture set number 6. The last topic in lecture set number 6 was cluster sampling with proportions that were proportional, with probabilities that were proportional to the size. So cluster sampling with PPS. We showed that effectively the estimators for the mean and the total under this approach were pretty much exactly what you would expect the estimators to look like. So the sample mean, for example, was just the average around, the sample mean was essentially just a weighted average of the mean from each of the clusters, and the variance of that estimator was essentially just an FPC type calculation multiplied by the typical variance of the mean estimator that you would expect from a simple random sample. So what I mean is you basically found the deviation of each cluster's mean around the overall mean, squared that, divided by the number of means, and then you corrected for population size. In lecture set number 7, which we also started on Wednesday, we're talking about sort of a mix mash of different components that address different issues within the sampling strategies that we have seen so far. Okay, so for example, The first two approaches that we talked about on Wednesday's class during Wednesday's lecture were direct sampling and inverse sampling. Direct sampling and inverse sampling are both techniques that we can use to estimate the population size. So throughout the lecture, we've been focused on estimating the population mean, the population total, the population proportion, some variable that represents or characterizes the population that we are studying. But we have seen that, for example, when we estimate the total, we need to know the population size. And it isn't always the case that we will have this information. So direct sampling and inverse sampling are techniques that we can utilize to estimate these quantities. So to find this population, to find the population total. And these approaches work, or at least the result from these approaches is very similar to the results that we have seen throughout the lecture. So we would have a point estimate, and then we would bound that point estimate, and we can do things like create a 95% confidence interval to see where the population size, or between what values the population size would fall. With that being said, we also are, oh, sorry, I lost my train of thought again there. So interval. Yeah, so with that being said, we're able to compute the interval, and then the examples that we utilized, sorry, that's what I wanted to say. The examples that we utilized to demonstrate these approaches were both based off of wildlife populations. So we utilize the idea of mobile wildlife populations that are consistently on the move to illustrate these approaches. So those would be examples where in a natural setting, you would be focused on only finding population size rather than, say, using it to estimate some total of a population. Okay, so just before I get into the new stuff, for the final, would we have an option to write it from home? Yeah, so it'll be, I'm gonna run the final exam the same way that I have the quizzes. So if you would like to write it from home, you can. Just please let me know. I'm gonna assume everyone is coming in unless I hear otherwise, the same way that I did for the quizzes. And then we'll just move forward from there. So it'll be run the same way that it was throughout the semester. So through CrowdMark, the only difference is that it's an extended time period. So you have from 9 a.m. until 12 p.m. to complete the quiz and submit your answers. Whereas obviously with the lecture quizzes, you just had from 9 a.m. to 10 a.m. Okay, so the topic that we left off looking at last class was estimation of a density and size via what are called quadrats. So we defined essentially an area, and we said that this area is going to be broken up into equal size components. So we have some piece of land, for example, that has a total area capital A. This piece of land can be separated into capital N components. Each of the capital N components has a size of little a. We let little mi donate the number of elements within each of these quadrats or components, such that capital M is the sum across all of the components of the number of elements within each component. And then we let lambda donate the density of the elements across the entire area, right? So lambda is essentially just the number of elements divided by the area of the place that you're studying, and we call that the density, where area can be measured in a variety of different units, but typical measurements for units are some metric squared, right? Like meters squared, or even square footage could define the area, centimeters squared, this kind of idea. So it's not all that different from a mean estimator. It's just the context in which we are explaining it is different, or utilizing it is different. Okay, so we can let little m bar designate the number or the average number of elements per the sampled quadrats. So little n represents the number of quadrats that we are actually pulling from this area. If little mi is the number of elements per sampled quadrat, then 1 over n multiplied by their sum is going to be the average number of elements per quadrat. So to estimate the density, which we call lambda, we have m bar over a, and we have the variance of our estimator as being lambda hat over a times n. From these formula, we can show that estimators for the total number of elements are given by lambda hat times the area. And the variance of this estimator is a squared multiplied by lambda hat over a times n. All right, so to illustrate this approach, we have the following situation. We have air samples of 100 cubic centimeters are sampled periodically from an industrial section of a city. Suppose the average particle count across 15 samples was 210. All right. Okay, so we want to estimate the particle density per cubic centimeter. So here we're going to have little a is equal to 100. Little n is equal to 15. Oh, wait. Suppose the average particle count across 15 samples was 210. Oh, sorry. M bar equal to 210. Across 15 samples, little n. All right. Okay, so from this information, we want to estimate the particle density. So we have lambda hat is equal to m bar over a. So this is going to be 210 divided by 100, which is 2.1. All right, and then we want to bound this. Okay, so we want to compute the variance of lambda tilde. This will be lambda hat over an. So this will be 2.1 divided by 100 times 15. 2.1 over 1500. Just check this one real quick here. And then our bound will be 1.96 multiplied by the square root which will be 0.078. Seven, four, eight, three. Yeah, there will be, well, essentially what I will do is I will post a practice problem set that is composed of problem types that you haven't seen so far. So the last practice problem set will have cluster sampling problems on it, double cluster sampling problems on it, some selected problems from this unit as well. And then in combination with the other practice problem sets, you can use all of that to prepare for the final. Cool. So does anyone have any questions about this stuff? I know it's probably pretty straightforward, but just in case. Yeah, it's a cumulative final. Yep. Any other questions? General questions? Like if you guys want to ask questions about the final now, I mean, it's already happening. So if you want to keep going, it's fine. I don't know. I haven't written it. Um, the last the last version of this final exam had um, 1, 2, 3, 4, 5, 6 questions. So the last time I gave this final, it had 6 questions, and there were 5, 8, 13, 13 subparts. So 1, 2, 3, 13. So around 16 total like questions with subparts. Is there more weight on the latter part of the course, or is it pretty evenly distributed in terms of content? So the last time I gave this final, I would say that it's pretty evenly distributed in terms of content. Sort of like just kind of like one question from each of the major units. Mix of proof, calculating, and explain something. Yeah, it has a little bit of all of that. We have mix of problems like some proofs and calculations. Yeah, you'll have a mix. Yeah. Any other questions? Questions. Questions will similar to what we had on quizzes, or will there be long computational questions like our assignments? Um, I wasn't planning on asking long computational ones, like where you would have to work out, the variance of the ratio approach, or something like extensive where you're summing across lots of observations at a time. So for example, you can expect questions where the required summary statistics would be given to you, and you would essentially be showing that you understand the sampling scheme that's being utilized, how to approach um, calculations for said sampling scheme. That being said, like the practice problem sets are typically longer to sort of force you to go through the process of performing all of the calculations. But I think it's fair to say that you should expect a similar setup to what you had on the lecture quizzes, where you're given um, any of the more tedious calculations would be given to you, so that you can focus on the direct application of the estimators that we have talked about. Yeah. Any other questions? Okay, not seeing anything. Just give it a second. Okay, do you guys have any other questions about the fourth assignment? The assignment goes to the end of lecture 5. Yeah. Any other questions? Will you have office hours after Monday? It's a good question, actually. I hadn't really thought about it. I'll have office hours on Monday. Um, to be honest with you, the office hours aren't very well attended, so I haven't noticed a lot of students using it. Students tend to prefer emailing and either just using email to resolve their questions or setting up individual meetings. So my preference will be the latter, in that I'll be happy to take any email questions. And if you would like to meet to discuss something, then we can just set up a time. Um, because like I said, it just doesn't really seem like the scheduled office hour is it really gets used. I just don't think it fits with everyone's schedule. So if you have a question, I'm more than happy to just work with you individually on it. So that's how I'll approach being available before the final. This is going to be a really funny lecture video of silence and a section of just random questions about the final. Okay, any other questions? And then of course the Zoom is frozen on me. Give me one sec. So I'm gonna just get back into the 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 lecture set. I'm gonna go as fast as I can to get as much material done as I can. No, I'm just kidding. All right, so we just talked about estimating the density of a particular region and then placing a bound on that particular estimate. We can do the same thing if we actually have an indication of how many elements exist on said area that you're studying or within each of the different quadrats. So we refer to a quadrat that contains the species of interest as being stocked. Okay. So we write here, little n is the number of sampled quadrats, little a is the area of each sampled quadrat, capital A is the area of the entire population, and y is the number of sample quadrats that are not stocked. So we can estimate the density and place a bound on that error. Just want to make sure 410, show the particles to be present. I don't know why I have this as not here. Oh, now my pencil's not working. There we go. R stocked. Okay, so to illustrate this idea, same idea as before, really. So we want to, okay, so for a sample of 500 cubic centimeters is taken from the industrial city reference in the previous example. If 410 showed the particles would be present, estimate the density, place a bound. Okay, so in this case, we have little a is equal to 100, which was the same value we used in the previous example. So we're using the same description that we had on slide 10. Okay, now we have little n is equal to 500 because we're told we have a sample of 500. And we have y is equal to 410, which are the number of stocked pieces of land. Okay, so we want to estimate the particle density and place a bound on said error. So we have lambda hat is equal to -1 over a ln y over n, which is equal to negative 1 over 100 ln 410 over 500. Oh, oh, I see what I've done here. Okay, so this is supposed to be not stocked. Sorry. Okay, that makes more sense. So then y is the number of unstocked areas. Okay, so this is going to be, there we go, 500 minus 410. Okay. And that is going to give us 0.0171. All right, and then in part B, we want to bound this thing. So we're going to have the variance of lambda tilde is equal to 1 over NA squared. One. Multiplied by e to the 0.0171. And that gives us 0.9.7 times 10 to the negative 7. All right, and then our bound will be 1.96 multiplied by the square root of the variance of lambda tilde, which is equal to 0.0019. All right. Okay, we should have time for one more. Any questions quickly? I'm scared to ask. Okay, so the next concept that we're going to talk about is adaptive sampling. As you can see here, adaptive sampling is essentially an approach that allows us to include new information within our estimation. So the idea of being adaptive means kind of like being able to intake information as it becomes available. Okay, so for example, we can use this when estimating the density of something rare. So you don't have a lot of information about it up front, but maybe as you go to study the specimen, you gain information, so you can include this within your adaptive sampling scheme. So we have here that the estimator under adaptive sampling is essentially a ratio estimator. So you have 1 over little n, which represents the number of samples being collected, of the sum of yi over mi. So yi is the total number of elements of interest that you have counted, and mi is the total number of, like I have, for example, here cells in each network. So this would be the total number of elements within each of the different samples that you have collected. And then we have our variance for mu tilde y is equal to 1 over, well, an FPC multiplied by sy squared over n. So sy squared, which I don't actually have written down here, is equal to the sum from I equals 1 to n of yi over mi minus mu hat squared divided by n minus 1. Cool. So pretty much just the standard estimator for a variance from any sample. Okay, so we have a random sample of 5 from 100 cells is selected, and an adaptive sampling scheme is proposed as follows. If a sampled cell has at least one maple tree in it, then the 8 neighboring cells are investigated as well. If any one of those cells contain a maple tree, it is added to the sample and its neighboring cells are investigated as well. Okay, so consider the following map and table and use it to estimate mu and the variance of mu hat. All right, so we have the following situation. So you can imagine here, this is going to be kind of like a grid area that we're studying. So we need to divide this into a 10 by 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, I was so close. Oh, that's not what I wanted. Okay, whatever. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so 1, 2, 10, 1, 2, 10. Okay, so we're going to say that 5 were randomly selected. Okay, so then it says to us, if a sampled cell has at least one maple tree in it, then the 8 neighboring cells are investigated as well. If any one of these cells contain a maple tree, it is added to the sample and its neighboring cells are investigated as well. Okay, so we have that yi is the total count of points of interest and mi is the number of cells in each network. All right, so for example, suppose that M1, which represents, well, I guess maybe I'll use the colors. So M1, which represents this cell, is equal to 1, all right? And this corresponds to a yi value being equal to 0. So what this is saying to us is that we investigated this first selected cell, which is this square with a 1 in it here, and we found no maple trees. Okay, so the contribution, the number of trees contributed is 0, and the number of cells that is utilized is equal to 1. Okay. So utilized cells, number of maple trees. Okay, then we explore the second cell. Okay, in this case, suppose that we have 4. So that means that we found a tree in the first cell, and then we branched out to each of the 8 surrounding cells. Okay. Now, let's suppose that in this case, y2 was equal to 4. That means that we found one tree in cell number 2, and then in the 8 remaining cells, we found a total of 4 other trees. So maybe one here, one here, one here, and one here, for example. But it could be in any of the 8 cells. Okay. So now it's the same idea with the remaining cells. So for example, with cell number 3, let's suppose here we have M3. This is again equal to 1. So we would have branched out. Okay. But in this case, we only have y3 being equal to 1, okay, which means that we only had a maple tree in that cell, and we could not find any in the surrounding. So M2 being equal to 4 counts the number of trees that were found in that like network. So we found one tree in the cell with a 2 in it, which meant that we branched out. And then we found 3 other trees in the surrounding network. So for example, one here, and one here, which gave us a total of 4. I didn't mean to sketch 5 points. Does that make sense? Okay, cool. All right, so then for M4, let's suppose that we have a network of size 5. So that means that we found at least one tree in the first cell. So we branched out. Okay. And then let's suppose in this case that when we branched out, we found a network, or we found 15 different elements. So that means that we actually have multiple trees being included. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, maybe something like that, just for illustration purposes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 6, 7, 9 plus 6, 15. Yeah. And then for M5, let's suppose in this case we have 2 different networks. Oh, wait, I made a mistake here. Can't do it like this. The network size is 5. So that means that 1, 2, 3, 4, 5, for example. There we go. Little 5 here. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There we go. No, that's 6. Damn it, Brian. There we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Then we'll add 1 there. There we go. Okay, and then in the last case, we have 2. So let's suppose that we have 1 here, and then I'll just put the other one here, giving us a total of 7. All right, so that would be 1, 2, 3, 4, 5, 6, 7. There we go. All right. Okay, so this is an idea of how the adaptive sampling scheme would work and how we would collect information by branching out to the other points. So the only thing we have left to do is to estimate the number of maple trees and then put an estimator for the variance on that. and then estimate the variance of said mean estimator for the number of trees. Okay, so I don't think, well, I'll just start it off real quick here. Oh, actually, okay, sorry. I'm just gonna have to move some stuff around. So I'll just start Monday's class by just going over those calculations very quickly. We're basically just subbing into equation 10 though, so this isn't an overly taxing calculation by any means. So we'll do that on Monday. That'll take about 5 minutes at the start of class, and then we'll start review for the final. Okay, so I'll post some practice problems. I'll send out some updates and reminders via Blackboard. Assignment 4 is still due this evening. And as always, if you guys have any questions, please let me know. And otherwise, have a good weekend, and I'll talk to you on Monday. M1 would still be 1 because we have one cell in the network. There's just 0 objects being associated with it. So we just assume these numbers. Yeah, I'm making these numbers up for illustrative purposes. But for example, if you were to be asked this on like a test, you would have the diagram and then you would go through and kind of work through the diagram following the explanation of how adaptive sampling works.